Okay, a cannon is fired horizontally from the top of a castle that's 20 meters tall. So we're going to draw kind of our castle edge wall or whatever with 20 meters. And the enemy formation's 120 meters away. We're looking for the velocity of the cannon. So I'm going to start with a picture so we can isolate all the things that are necessary and get an idea of what's going on. And then anytime something's moving both in X and Y, we want an XY table of those variables. So now that we have the visual, we can create that XY table where our displacement's 20 meters down and 120 meters horizontally. When I'm looking at determining direction and which direction is positive, which one direction is negative, I'm going to say the first direction it moves is positive. That being to the right is positive and down is positive. 120 meters would be my delta X. My delta Y is at 20 meters. If you want the acceleration down to be negative, you need to also make the displacement 20 meters down negative. I think it's simpler just to make it all positive if it's only moving in one direction. Here we've got a displacement of 20 meters, initial velocity of 0 vertically, and acceleration vertically of 10. Time is shared between the two columns, so if we solve on the right side, because we have 3 knowns, if we solve on the right side for time, we can move it to the left. Then we would have 2 knowns on the left, allowing us to solve for the velocity of the cannon horizontally. Delta y is equal to v naught t plus 1/2 at squared. V naught is 0, so v naught t is 0, leaving us with delta y is equal to 1/2 at squared. Multiply both sides by 2, divide both sides by a, and then square root both sides, and that will isolate the t on the right side. The square root of 2a, or the square root of 2 times delta y, 2 times 20, divided by 10 is t. So 40 divided by 10, square root of 40, or square root of 4, so you get 2 seconds is your time. The range, or delta x, is 120, and that's equal to vx times t. So delta x divided by time is equal to vx, or the velocity in the x direction. 120 divided by 2 is going to be 60 meters per second. That's how fast it shot out of the cannon. Two bullets are fired from the top of a building that is 50 meters tall. The first has an initial velocity of 100 meters per second, and that's horizontal. The second, horizontal velocity, 150 meters per second. How far apart are the 2 bullets when they land? Well, they're both being shot horizontally. There is no initial vertical velocity. They're not shooting them down, they're not shooting them up, they're shooting them horizontally. That means that they both have an initial vertical velocity of 0. They both are under the influence of gravity, 10 meters per second squared downward. They're both going to fall 50 meters as they move forward. So their vertical components are all identical. They share the same information vertically. V naught is 0, acceleration is 10, delta y is 50. Again, if you want down to always be negative, your delta y needs to be negative 50, your acceleration would be negative 10. I'm going to keep it all positive because that's the only direction it goes vertically. Here we want to solve for time so we know how long they're in the air. Much like the last problem, delta y is equal to v naught t plus 1/2 at squared. Write the equation every time. It'll help you learn it so you don't have to look it up and waste that time looking through a formula chart in the future. V naught is 0, so v naught t is 0. It's gone out of the equation. So we've got delta y is equal to 1/2 at squared. Multiply both sides by 2, divide by a, and then square root to isolate the t. So we have the square root of 2 times 50 divided by 10, all square rooted. So we've got the square root of 100 divided by 10, or otherwise known the square root of 10. Square root of 10, we know it's going to be just more than 3 because 3 squared is 9. So we're anticipating a number around 3 point something, so 3.16 seconds is our time. Each bullet's going to be in the air for 3.16 seconds. One is moving at 100 meters per second, another at 150 meters per second, so we're going to use our delta x, our range, is equal to velocity times time for each one separately, and then subtract them. So we have 150 times 3.16, and then the other bullet, we've got 100 times 3.16. So our first one, 150 times 3.16 is 474, and our second one would be 316. So one bullet's traveled 474, the other traveled 316, both in the same direction, so we'll subtract those distances, those displacements, and that'll tell us how far apart they landed. 474 minus 316 is 158 meters. Final problem on this page. Bubba Joe fires a rifle in the middle of the flat desert. So Bubba Joe's shooting a rifle, and then Joe Bubba, his brother, is just simply dropping a bullet. So we have a bullet being dropped, another bullet being fired horizontally, both from the same height. The bullet that's being dropped takes 0.38 seconds to fall. Since they both have an initial vertical velocity of 0, they have the same distance to fall, same gravity acting. We know both share the same time of 0.38 seconds. The bullet being fired, Vx, is at 450 meters per second. And then how far away? Well, the drop bullet's at a 0 displacement horizontally. So we just need to find out how far away that bullet goes. Delta x is Vx times t, or delta x is 450 times 0.38. So our delta x, our displacement, is going to be 450 times 0.38. We get 171 meters. Onto the back page. Now we're looking at kinematics where we're firing things at angles. So we've got to break apart the velocity into its components, the horizontal component and the vertical component. When I'm doing the components, I like to do the dashed lines. It helps separate things. So the cannonball comes out at 100 meters per second, but we need to see what is horizontal and what is vertical. So the horizontal component will be the Vx, and the vertical, that's the initial vertical speed before any gravity grabs a hold of it. So Vx horizontally is going to be calculated as the hypotenuse function angle, and then the vertical is also going to be hypotenuse function angle. For horizontal, it's adjacent, so we're using cosine, and for V naught, it's on the opposite, so we're going to use sine. Make sure your calculator is in degree mode. Vx would be 100 cosine 30, and V naught is going to be 100 sine 30. And I'm just going to go ahead and start building my table. I usually need it. I may not on this one, but I'm going to go ahead and build it so I've got that information there. So I've got Vx, 100 cosine 30. I think that's going to be like 86.6. And then 100 sine 30 is going to be 50. I'm just going to squeeze those into the table just as quick as I can calculate them and type them in. Okay, so what is the acceleration in the x direction? The acceleration in the x direction, well, there's nothing acting in the x direction after the cannonball comes out of the cannon. Gravity's the only thing acting, and it's vertical, so there's nothing. What is the initial velocity in the x direction? Well, the velocity in the x direction is permanent, so it's not going to change, and it's calculated as 100 cosine 30. The hypotenuse function cosine times the angle. And we got 86.6 meters per second. What is the acceleration in the y direction? Well, it's gravity. It comes from gravity, and we're calculating that as 10 meters per second squared downward. Since the initial velocity is up, I would make this negative because it's in the opposite direction. It is changing direction. What is the initial velocity in the y direction? Well, that's our v naught, and we said that that is 100 sine 30. That's the hypotenuse function sine times angle, and that was 50 meters per second. What is the final displacement of the ball in the y direction? So they're asking about delta y. Final displacement. So where did it start and where did it end? That's what we need to consider for displacement. And at the top, it tells us the ball lands at the same height. If it lands at the same height from which it was fired, it has a 0 vertical displacement in the y. How long is the ball in the air? Okay, that's total time in the air, from time it launched to the time it hits the ground, so we're looking for t. The initial vertical velocity is 50, so the final is going to be negative 50, same height, opposite direction. Acceleration being negative 10. Since the initial velocity is up positive, acceleration is down negative. This looks like we can use our VOTAT equation. V is equal to V naught plus acceleration times time. Let's rearrange for time, so we're going to subtract V naught to the other side and then divide acceleration to the other side to isolate the t. V negative 50 minus V naught 50 divided by negative 10 acceleration. We would get negative 100 divided by negative 10. So we should get 10 seconds. What is the range of the cannonball? The range is delta x. Delta x is the range, it's how far it goes. So we're looking for delta x, and we know delta x is Vx times t. So let's look up for our Vx. Looks like it's 86.6. We calculated that earlier, so let's go ahead and put that in. And then the time, we got the time just a second ago at 10 seconds. So delta x is Vx times t. Delta x is 86.6 times 10. So our range should be 866 meters.